Hello all, welcome to the Tektronix USB4 Compliance and Characterization Test Challenges webinar. My name is Abhijit Shinde and I am the USB and DisplayPort System Engineer at Tektronix. Let's begin with the disclaimer. All the product names used in this presentation are trademarks of their respective owners. The USB4 electrical compliance and certification test should follow the USB4 electrical CTS. So here is today's agenda. First, we will walk you through the what's new in USB4. Then second session, we'll discuss the new test requirements in USB4 and the corresponding challenges. In the third section, we will discuss the transmitter and receiver characterization. In the fourth section, we will discuss the virtual probing. The fifth section will walk you through the USB4 electrical requirements. And the final session, we will discuss the Tektronix USB4 solution offering. Let's start with what's new in USB4. In the USB4, there are two data rates, 10 Gbps also referred as Gen 2, 20 Gbps also referred as Gen 3. Now USB4 can be integrated directly into CPU. But if the product supports USB 3.2 or USB 2.0 functionality, then a separate discrete controller chipset still needed for USB 3.2 and USB 2.0. The USB 4 also introduces 16 new presets, meaning 16 different combinations of transmitter equalization. It's a big change from the USB 3.2 transmitter, which supported one pre-shoot level and 3 de-emphasis levels. In the USB 4, host-to-host communication is possible using the dual-role data operation. One of the big difference in the USB 4 receiver testing and the link initialization or lane initialization is now it is using the sideband channels to do the communication. And the receiver testing, the USB 4 receiver testing is different compared to the traditional USB 3.2 receiver testing. Now the USB 4 receiver testing is using the onboard error counter to count the BER. So now we need USB 4 controller to perform both transmitter and receiver testing. Let's understand the test points and channel budgets in USB 4. The USB 4 allows total of 6 retimers in the USB 4 link. This is to maintain the signal integrity. So 2 retimers are allowed in the router host or router device assembly. And if it is an active cable, 2 retimers are allowed on the active cable. Also note that the router host or router device assembly channel budgets are now informative in USB 4. But the good news is when we are performing the test, the compliance test for the USB 4 that is performed at TP2 and TP3 test points. And the connection or setup remains same for both TP2 and TP3 test points. So we will use either the plug fixture or receptacle fixture and directly connect it to the device under test. And 1 meter, maximum of 1 meter cable can be connected between the fixture and to the scope. And this cable is allowed to de-embed it. And when we perform the TP3, we embed the cable model, worst case cable model. So when we are doing the USB 4 10 Gbps Gen 2 test, we embed the 2 meter cable. And when we perform the USB 4 Gen 3 20 Gbps test, we embed the 0.8 meter cable model to make it TP3 test points. Also note that when we are performing the TP3, those are using the equalization. that is combination of CTLE and DFE. In this section, I will walk you through the new test requirements in the USB4 and the corresponding test challenges. The first test is transmitter preset calibration. It's a prerequisite step for transmitter testing. In this test, we capture all 16 preset waveform and then we measure the data deterministic jitter, DDJ. And the one provide us the lowest DDJ value is selected as optimal preset. So in this example, I have P1 as my optimal preset. So all my transmitter compliance testing will be performed with P1 only. And to burn or flash the platform with the optimal preset, you might need NVM tools. In the lane initialization process, a transmitter starts with the optimal preset or the initial preset, but the receiver might ask a different preset that is not the optimal preset or that is not what is been tested. So it's a good idea to validate and measure all other presets and perform the transmitter testing. So this test also we need to be performed on both the lanes and for both the data rates. The second test is transmitter equalization test. Again, this test is related to USB4 presets. The objective of this test is to make sure the transmitter equalization falls within the specification limits. So this test requires 3 waveforms per presets. Waveform 1 with de-emphasis and pre-shoot on, waveform 2 de-emphasis on, pre-shoot off, waveform 3 de-emphasis off, pre-shoot on. And given the formula, we measure the pre-shoot and de-emphasis. So that's total of 48 waveforms. Another 2 waveforms we need to measure the swing for preset 15. If you have noticed the coefficient over here, if you do the absolute sum of this coefficient, that's not equal to 1. That is because it's a reduced swing. Also note that preset 14 is recently changed. So if you are implementing the preset 14, make sure it is using the correct values. Let's switch to USB4 receiver testing. First, USB4 receiver calibration. The USB4 receiver calibration need to be performed for all 5 SJ frequency. That's a big change compared to USB 3.2 receiver calibration, where we used to perform the calibration only for 100 MHz, and then we used to use the same calibration for the receiver testing. Also in USB4, there are 2 test cases where we need to do the auto tuning or fine tuning to meet the I or total jitter targets. The case 1 is the low insertion loss. Case 2 is the maximum insertion loss. If you have noticed, the total jitter targets are provided in the USB4 base specification for both case 1 and case 2. But if you look the method that is in the USB4 CTS, we just fine tune the I diagrams, but we actually don't measure the total jitter in the case 2. So the I adjustment is done using the RJ or SJ based on the SJ frequencies. Let's understand the USB4 receiver test challenges, or how we can run the traditional jitter tolerance test in USB4. One of the objective of jitter tolerance test is sweep the SJ or amplitude and find the boundaries or find where the errors starts coming. So to perform this test, we need to first initialize the link using the sideband channel, and then we need to start the BR test, and then we need to keep on monitoring the errors, as now the USB4 is using the onboard error counter rather than the traditional error detector on a board. So this will be a multi-step process, and for each step size increase, we need to we need to see whether there are error occur or not. If error occur, you can reduce or increase the step and go to the next level. And once we fine tune and find the boundaries, then you can run for a longer duration for BR12 or BR9 duration. In this section, we will talk about characterization and how to get into the details. Here is an example of performing the transmitter test with 22.5 dB loss at 10 gigahertz, and having that confidence that it will be surviving the maximum loss available with the USB4 link. As the USB4 compliance testing is performed at TP3 point, not at TP4, you still need to do you have to go beyond compliance and find whether the product is going to survive within drop testing or the scenarios like when there are no retimers available in the link. So for an example, we have here is USB4 link without any retimers or redrivers, just for example like this. So when we are doing the TP3 test, we have total insertion loss of around 16.5, so 7.5. That is, even though it's informative, but it's still there in the router, and 1 dB is from the fixture, and 8 dB loss that we embed the worst case cable model on the scope. That becomes its TP3. So these are the eye diagram I got for the TP3 test point. And what I did is I just took the same TP3 waveform and I embedded another 6 dB and make it 22.5. That will be the maximum loss we can have in the USB4 link. And still use the TP3 mask because we wanted to compare how much margin we have if we embed additional 6 dB or 7 dB. Do we have anything challenging, or do we have the margin or not? One thing you can notice here is which is quite obvious, that CTLE for TP3 and TP4 is different, and we need additional CTLE to overcome that additional loss we are injecting. But good point is I still have a pretty good margin, and that's the confidence we need to build to know the product will survive with the worst case scenarios in the real world. Now let's take an example of receiver characterization. So one of the objective of performing receiver testing is to identify whether the receiver is auto-adapting and requesting the right preset, and it's going to survive the stressful eye, whether it's able to open up it, and is it PR free or not. So we have in the compliance testing two calibration sets. One is the low loss and another is maximum loss. But let's consider again a scenario where we have a device under test, and then we have a flash drive. That's a real-time scenario, and both don't have any retimers or redrivers in it. So how we can mimic that? So that's something we have in USB 3.1 or 3.2. We used to call it short channel test. So I just come up with the calibration and concept for the short channel test. So what we will have ISI channel, which will be like 5.5 dB to 6 dB at 5 gigahertz, and then 7.5 to 8.5 dB at 10 gigahertz loss. And so this condition will mimic the short channel scenario. So one of the things why we need to perform the receiver testing at different calibration is to make sure the receiver adaptation, the receiver equalization and CTLE works well, not only for the lowest insertion loss but the highest insertion loss, because we have seen the cases in the past that people will fine-tune their receiver in considering always the long channel, and then it will overcompensate or over equalize the signal, and it might fail the short channel or the no channel cases. In this section, we will talk about the virtual probing and how it can help to build a greater insight. Let's understand why we need virtual probing and how it will benefit us. So one thing is important to see when you are doing the transmitter test is compare the results at different test points and see how it behaves at, let's for example, TP2 and TP3, how it behaves. And if we don't have margin at TP2 itself, and then we don't need to, we will definitely, it will fail at TP3. So we need to find a root cause. So we can root cause the issues at TP2, not at TP3. So there is something wrong with the transmitter path, or there is something wrong happening in this path that is causing TP3 failure. Another important aspect of virtual probing is using the IBS AMI model in the receiver equalization. So that means use the CTLE and DFE adaptation as implemented in the receiver and see how those jitter numbers looks like and what is the best CTLE coming out. It's always on how it is equalizing. It is over equalizing or under equalizing, or it is optimal equalizing. Another important thing for the virtual probing is when we are starting uh, the using the reference board or reference design, sometimes that doesn't have a connector. It might have the probing where we can probe it and see it. But how to make sure we are close to the compliance testing, or how we can do the testing that is to the real life or real world. So we can embed the fixture model and embed the compliance channel to make it a TP2 and TP3 and give that effect of connectors, the reflections, and make it TP2 or TP3 test points. And one of the other aspect is you need a toolkits to see the waveforms or data side by side at the same time. So you can play with it and you can modify, and at the same waveform you can see how things are behaving, rather than capturing two different waveforms and performing analyzing and then correlating. Is it run to run variation in the DUT, or is it what is the root cause of it? So it's always good idea to have a single tool that can perform at different test point that allows you to configure different sources, and you can configure the CDR settings each individually for each measurement. So we can root cause and fine tune the issues using the virtual probing capabilities. Let's understand the USB4 electrical certification requirements. Here is the USB4 electrical certification test requirements, and it varies depending on what the product type is. So let's say if we have designing a host, we need to perform the USB4 electrical, USB 3.2 electrical, USB 2.0 electrical, DisplayPort 1.4 or 1.2 depending on what you are implementing, and then Thunderbolt 3 compatibility mode. If it is supported, that electrical testing still need to be performed. Device, depending on what it is supported and implemented, that testing need to be done. But if it is hub or dock, you need to support all, and all the electrical testing is mandatory. So for USB 4 transmitter and electrical, the scope requirement is 21 gig and above. In this section, I will just walk you through the Tektronix USB 4 solution and what is the Tektronix offering. Tektronix USB 4 solution can be used for design validation, for debugging, and as well as the compliance testing. As most of the time we need to do beyond compliance testing, we need the tools to do the debugging or to do do the more design validation and see how the things looks like, not only with the compliance testing, but beyond compliance testing. So we call a DPOJET, that's a Tektronix jitter and analysis measurement toolkit, and we have options, so user can go and modify the CDR options, the filter options, or we can add the plots which the cursors are mapped to the waveform to find the issues and to do the more root cause analysis. The virtual probing and customization is using the Tektronix STLA tool, which supports de-embedding, embedding, equalization, and IBCMI model simulation as well. So we have today the Tektronix compliance test solution available with fully automated USB4 ETT tool and the Wilder controller. So it's a single button solution that controls the DOT and validates the signals. If it is failing, that will prompt you the message to the user so that user can take the corrective actions, and it will generate the reports in PDF HTML formats. We also do the offline analysis, and one of the things is important as we are keep on changing, we need to create the golden baselines and references. As sometimes the CTS changes, there is no test methodology comes. So we always need to find what is the delta. Is that delta is due to my product variation, or is it due to the new measurement or new analysis toolkit? So it's always good to have your product supports a pre-recording mode or offline analysis. And the Tektronix both debugging and then compliance tools supports the offline analysis, or we call it pre-recorded mode. It has been supported. Thank you for attending. Let us go for Q&A session. Thank you.